Okay, so reactions in aqueous solutions. Okay. Are we all together? Yeah? We're all together? What do you know about reactions in aqueous solution? Let's start from the very beginning. We have this concept of matter, and we've broken matter out two ways. What were the two ways that we broke down matter? Mixtures and versus if something's not a mixture, it would be considered a pure substance. Okay, so if something is a pure substance, what are the two breakdowns for the pure substance? And this is just recap. An element, who said that? Versus a compound. And so an example of an element would be carbon, for example, or any of the other elements we take a look at on the periodic table. So they're single entities. And an example of a compound would be water. So you take the element oxygen and hydrogen and combine them in some way to form a compound. In mixtures, how did we parse the term mixtures? There are two kinds. They're homogeneous versus heterogeneous. And how do we distinguish between the homogeneous versus the heterogeneous mixtures? The same from what point of view? The same? Throughout, so visibly. We look at it and it has a uniform appearance versus a non-uniform appearance. So an example of a homogeneous mixture would be tea, for example. You have tea and water, or salt water as another example, and an example of heterogeneous mixture. Orange juice, salad, so on. So now under this category, we're going to take this category, we take a mixture that's homogeneous and form the basis for this topic. So a homogeneous mixture, you can create a solution from it. So this category of solutions, so this chapter is entitled Reactions in Aqueous Solutions. We'll get to aqueous in a second, but in general, the solution falls under the umbrella of a homogeneous mixture. And so by definition, a solution is a solute plus a solvent. And so by definition, what is the solute? The thing you put in the liquid. By definition of this combination, it's the lesser amount and the greater amount. So it's the thing, so someone said the thing you put in the liquid. Are you then assuming that solutions only have one state? What are the states that solutions can be in? All of the ones we know. It could be solid, liquid, gas, and in a second, aqueous. So these are the parentheses we put next to the species when we start writing those reactions. When we write the chemical reaction, reactant, dash, product, we'll have to identify what each of the species looks like. Okay, so if any solute and solvent combination makes a solution, the thing that makes something an aqueous solution is to identify this solvent as water. So it's a solute plus water, giving you an aqueous solution. So it's something that's diluted in water to give you the aqueous solution. Okay. So then, if you have your aqueous solution that has two branches, how can you parse an aqueous solution? What kinds of aqueous solutions can you have? I'll give you a hint. Gatorade? Gatorade would be an electrolyte solution versus a non-electrolyte solution. So electrolytes versus non-electrolytes, what is the difference? One has electricity? Electrolyte implies that there is some charge-charge relationship governing the solution. So you're kind of on the track, but what is the solution actually made up of? Right, so your solute in an electrolyte solution would be an ionic compound. Versus the non-electrolyte, the solute, would be a covalently bound compound. Okay. So if something is ionic versus covalent, how do you define those two terms?
Ionic has a charge, so it would be a metal and a non-metal, as opposed to molecular or covalent would be either two metals or two non-metals.
Okay, so to translate what she just said, when we're defining this electrolyte versus non-electrolyte, ionic versus covalent, we're basically looking at the nature of the bond. If the thing that draws the two pieces together is because of an electrostatic interaction, you have an ionic compound. If the thing is the sharing of electrons, you have a covalent compound. So let me give examples. What is this compound? Sodium chloride, which is table salt. And we know that what group does sodium belong to? Group 1. And so if it takes on an ionic nature, what does it look like? Na plus 1. What group is chlorine in? And so if it takes on an ionic relationship, what does it form? And so when you have a metal, like you said, metal, and a non-metal combining to form an ionic compound, this metal, if the metal becomes a cation, that's indicated by the positive charge, and the non-metal becomes an anion, indicated by the negative charge, the thing that's binding them together to form NaCl is an electrostatic connection between this plus and minus charge to form the neutral. And so this is an ionic solution. What is covalent? Let's take, what is that? Water. Does it form ions naturally? It does in some instances, but in this water combination. So if you look at water, you basically end up with this arrangement for water. The bonds here indicate that there's one electron from the hydrogen, one electron from the oxygen, and they're being shared. And so this is how you form this OH connection. Same on this side, one electron from hydrogen, and one from oxygen and one from hydrogen, and again, that's shared. So it's the sharing of electrons makes the bond covalent. So now, how does this have anything to do with solutions? So the nature of solutions is, if you have something that's ionic going into solution, what happens is these ions dissociate from each other and float around in the solution loosely. And that floating of charge in solution is what creates this electric component. So have you done the lab where you take a light bulb with 2 electrodes sticking out of it, and you immerse it in what you think is an ionic solution, and bing, the light bulb goes on very strongly. Because what you're doing is there's a movement of charge. So if you have electrodes to a light bulb, if there's a movement of charge in the solution, you're basically creating a wire that closes the circuit, and so then you'll get the bulb to go on if you have a solution that's able to have charge flowing. And only solutions that are ionic are capable of doing that. Covalent solutions stay as whole molecules. They stay as neutral species in solution. So there is nothing that creates a wire to close the circuit, so you immerse this electrode into sugar water, for example, and your light bulb stays off because this circuit, this wire, isn't closed. And so that's the nature of the electrolyte solution. It's electrolyte if it can create electricity by closing this circuit. That's one hint that you're dealing with an electrolyte. So electrolytes then can be categorized by strength. They're either strong or weak electrolytes. So what then would be the difference between a strong electrolyte and a weak electrolyte?
A strong electrolyte has a stronger charge, whereas a weak electrolyte will have a weaker one. So the stronger one will be in the top of group 1, and the weaker one will be in like the bottom of group 1.
Not quite.
The strong one has more ions floating in it.
Getting closer. More ions floating. So in formal terms, what do we call more ions floating? That means something that's a strong electrolyte 100% dissociates in solution. So what do I mean by dissociate? Let's take our sodium chloride example again. If I put this in solution, I form Na plus and Cl minus. Every molecule of sodium chloride will dissociate into Na plus and Cl minus. That's a sign of a strong electrolyte, 100% dissociation. Something that's a weak electrolyte only partially dissociates in solution. So if I go back to your definition, there are less ions floating. So fewer ions will be floating. Okay. Any questions so far?
Yeah, what causes the disassociation? Like what?
By the nature of what the compound is. Usually if you have things that are formed between metals and nonmetals, so group 1 and group 7, or group 2 and group 7 or 6, those will be stronger electrolytes than, for example, something that looks like, if you take it will only partially dissociate into CH3, CH2O minus plus H plus. So it's the nature of the compound that you're dealing with. Yeah, any more questions? Okay, so again, we're trying to get to this reactions in aqueous solution. And so the reactions we're talking about, we actually have certain forms to write it in. You can write a molecular equation that indicates the reaction of interest. Using the definition of whether it's strong or weak as an electrolyte or just covalently bound, you can then write an ionic equation. And then you can define the net ionic equation. So what's the difference between these three kinds of equations? So the molecular equation will have a reactant 1 in some form, some state. Reactant 2 in some state, going to product 1 in some state, and product 2 in some state. So when you write a molecular equation, reactant 1, reactant 2, product 1, and product 2 will have its normal molecular structure, H2O, for example. So you start with the molecular, where all the species are in the normal chemical existence. Ionic, you then have to determine what the solubility of each species is in order to figure out whether it will form ions or whether it will stay as whole molecules. And then the net ionic means that you've parsed out what's called spectator ions. And once you cancel out the spectator ions, what remains is your net ionic equation. So the example I'm going to do relates to experiment 5. How many of you have done experiment 5 in lab already? Okay, maybe it's easier. Who has to do experiment 5 next? Oh, you've all done it. Okay. No, it's reactions in aqueous solution. Yeah? Okay, so lead 2 nitrate is added to an aqueous solution of potassium iodide, a yellow precipitate, lead 2 iodide. Okay, so the question says lead 2 nitrate is added to an aqueous solution of potassium iodide. A yellow precipitate of lead 2 iodide is formed. So what's important here are a couple things. We're going to go from the words to the chemical formula based on what you remember of the nomenclature. Then we'll look at what's the reactant based on what's written here, figure out where to draw the arrow, and then put what's our product. And basically we're predicting our products based on what's here. So the first order of business, how do you convert lead 2 nitrate to chemical symbolism? Any volunteers? I have a volunteer?
It's PB and it's nitrate NO. Yeah, 2 minus, but then the charges switch, so there's parentheses on the nitrate.
What's lead 2 plus? What is, sorry, what's lead 2?
It's 2 plus, the charge is 2.
And what's a nitrate?
NO 3 minus.
So a polyatomic anion. Nomenclature is going to be very important going forward. So you should know that there was a lab of 3, I believe, that was all about nomenclature. This should be ingrained by now. So lead 2 is a lead 2 plus cation. The nitrate, NO3 minus. So if you do basically conservation of charge algebraically, how did Dr. Chang teach this? Did he teach it algebraically or crossover method? Okay, so the easiest way is take the charge from the cation and make it the subscript of the anion. Charge from the anion and make it the subscript of the cation. So you're forming PB NO3 2. Everyone see that? So you know how to do that by yourself? Okay. Do the same thing for potassium iodide. What group is potassium in? So it forms what cation? What group is iodide in? And so it forms? And so if you were to write the compound? Okay. And how do you convert lead to iodide? Yes? So the lead 2 is Pb2 plus, iodide is I minus, PbI2. Now we can write the molecular equation. What is the molecular equation? So if I say lead 2 nitrate is added to an aqueous solution of potassium iodide, I would write why do I put aqueous next to the Ki? It tells me it's an aqueous solution. What do I put next to the PbNO3? Do I? How do I know it's solid? Lead is solid, but when it's with nitrate, is it solid? Pardon? Now we're guessing. Let's go to the text. So table 4.3, I believe it's page 122. So how will you look up the solubility table? Oh, pull up your solubility table on Alex. Okay, so this table is going to be important to you to figure out what to put here, because it's the solubility of this compound that tells you whether it's going to be a solid, liquid, or aqueous that you need to write in these parentheses. So we'll get to that in 1 second. I'll give you a second to find that table. What is the product? It says a yellow precipitate of lead 2 iodide. So of course, since this is formed, it's on my product side, so I'll put my lead 2 iodide there. And because it says a precipitate is formed, this is a kind of, this is a feature of a reaction, a solution. A precipitate means a solid comes out. So if you mix 2 chemicals together and they no longer look homogeneous, but now they become heterogeneous, it means one of your products is a precipitate, and that state of matter of the precipitate happens to be a solid. So precipitate reactions produce a solid in the product. Is that the only product that I can get out of combining these 2 things? Pardon? Potassium nitrate from here? just leave it KNO3. Like that? Yes? And what state of matter would that be? We still don't know because we haven't looked at our solubility table yet. Okay, so now where our solubility table comes in handy. The rules of solubility depend on what the compounds are. And so looking at table 4.2, it gives you some valuable information. Basically, it says a compound is soluble if it contains anything from group 1. Rule number 1 for solubility. The second rule for solubility, nitrates, like this one, acetates, bicarbonates, chlorates, and perchlorates, those are all soluble. The third rule, halides. Halides are in group what number? 7A. Halides, like, example, fluorine, iodine, chlorine, bromine. Those are also soluble, except when they're coupled to silver, mercury, or lead. So if a halide is soluble, except when it's coupled to lead, from this table we could have predicted that this was going to be our solid without the question actually telling us that a precipitate of this forms. It says nitrates are always soluble with no exceptions, so I'll put aqueous here. Nitrates, again, are always soluble without exceptions. I put aqueous here. So now we have a reaction in its molecular form with all the states of matter. Are we finished? What's missing? Balance the chemical equation. How would I go about balancing this? So to balance chemical equations, now that we've put in all of our subscripts based on what the charges are, we basically need to fill in these boxes, right? How do I balance this chemical equation? I have a volunteer?
Ki has 2.
That's it?
Oh yeah.
And that's it? Everyone agree? Anyone have questions about how that happened? It's not balanced? Okay, let's check. So to balance the chemical equation, we need to make sure our reactant number of species matches our product number of species for each species. So we need lead. We need the nitrate because the nitrate is a polyatomic, so that stays together. We need the potassium and the iodide on both sides. Okay, so lead here, 1. Everyone agree? The nitrate here, 2. So this 2 tells you there's 2 nitrates, and this 2 tells you there's 2 nitrates. So nitrate looks okay. Potassium, 2, and this 2, so that's okay. And iodine, 2. Everybody's consistent, so both sides are balanced. And that's the exercise you kind of go back and forth on just to balance a chemical equation. Okay, so if this is our balanced molecular equation, how would you determine your ionic equation? So this is where the definition of electrolytes in solution come in. If your solute is ionic, it will dissociate in solution, and that's what this aqueous symbol means. It means it's already dissociated. So did you already cover hydration? No. Okay. So let's look at what's happening in the solution itself. When an electrolyte like NaCl dissociates to Na plus and Cl minus. So now we have the beaker. What's actually happening, so this is an aqueous solution. Aqueous solution implies that your solvent is water. Water has this special feature. It's known as a polar compound. Because what makes up water is a slightly positively charged hydrogen here, a slightly positively charged hydrogen there, and a slightly negatively charged oxygen there. So because oxygen is on the right of the periodic table, if oxygen were to form an anion, what does it normally form? O2 minus anion. So it has a negative charge that it likes to associate with. It's on the right of the periodic table. Hydrogen is on the left of the periodic table, so it likes to form this kind of positive, it has a positive nature. So the fact that you have a slightly positive and a slightly negative charged species, but they're covalently bound, there forms a charge direction of this molecule. And it's written usually with a dipole symbolism. So there is a plus sign near the thing that's positively charged and an arrow near the thing that's negatively charged. So I can write basically this kind of arrow. The arrow basically is parallel with the bond, the covalent bond. So I can write a second one on this side. So you have two dipole arrows going in this way. If I were to sum up these two dipole arrows, I get an overall polarity going in this direction. So the bottom of the molecule is slightly positive towards a more negative end of the molecule. So because water has this polar nature, when it's the solvent around some ions, these like to create what I call dance partners. The hydrogen part of the water points towards the negatively charged chlorine and surrounds it, and the oxygen part of the water points towards the positively charged sodium. So you end up with something like this in solution. There's a sodium, and it's usually surrounded by the oxygen part. And then there's a chlorine, and it's usually surrounded by the hydrogen part. So it's like dance partners. And this is what's called hydration. The negatively charged oxygen hydrates the positive cation of sodium, and the positively charged hydrogens hydrate the negative chlorine anion in solution. So this whole process is hydration. And this is how you get things to be homogeneous in solution. You're fragmenting a crystal of salt, surrounding it by species that prevent it from getting to its native partner from the solid, and now you've created hydrated versions of this. And that's hydration. So when you're looking at basically a molecular equation to try to figure out how to write your ionic equation, you can then assume the things that you determine to have aqueous nature will separate out into ions once they're in solution. So you write your ionic equation as follows. Pb 2 plus NO3 minus, and this is all aqueous, that's all aqueous, plus K plus aqueous, plus I minus aqueous. 2, what happens in this case where this is a solid? So our solubility table says that halides are soluble except when they're coupled to lead, making them insoluble. So when the product is a solid, it stays as a solid even though we're writing the ionic equation, because it tells you that that thing does not go into solution. like that. And then, since this is aqueous, again, you have K plus aqueous, NO3 minus aqueous. Is it balanced? Yes? You can do 2 here, 2 here, 2 here, 2 there. Now, is it balanced? Yes?
So, but isn't lead on its own a solid?
Not when you're starting with aqueous lead. So this isn't lead like Pb neutral. This is lead cation. So in solution, so all of these, this entire chapter, we're talking about things in solution. So you're just trying to figure out what state it will be. So it's still a homogeneous solution.
So why doesn't the iodine and the lead like split up?
Because this is insoluble. From the solubility table, if you have a halide, it's normally soluble except when it's coupled to lead. It becomes a solid and it drops out of your solution as a solid. Is that clear? Yes? So now your ionic solution, your ionic equation, is a balanced chemical equation which illustrates which species break out into their cations and anions once you have them in solution. Yeah? So now we look for what's called spectator ions. Spectator ions are the things that appear in the same amount on both reactant and product side. And so you can divide them out, just like dividing 2 sides of an equation by the same number. So if you want to divide, if you have any equality, 2 plus 3, 2 plus 3, if you divide both sides by 2, those drop out to 1, right? So that's the same thing you're doing with spectator ions. So look for spectator ions. So what would be a spectator ion in your ionic equation? Okay, so there's a 2K plus on this side and a 2K plus on this side. So those can drop out to 1. There's a 2NO3 on this side and a 2NO3 on this side. That can drop out to 1. Anything else? That's it. So now you're left with Pb 2 plus aqueous plus 2I minus aqueous produces PbI2 aqueous. And this forms your net ionic equation. So the net ionic equation by definition is your ionic equation minus the spectator ions. And that's what's left. Questions? Okay. So how about we try this one? So is this similar to what you did for lab 5? Yeah? Okay. So then I'll leave you to try this for about 2 minutes. Predict. Okay. Predict the precipitate produced by mixing an aluminum nitrate solution with sodium hydroxide solution. So write basically the molecular equation. What does that look like? So let's start off with a little bit of nomenclature. What is aluminum nitrate? Al3 plus and NO3 minus, so the compound is? Okay. And sodium hydroxide? What state of matter am I putting for my aluminum nitrate and my sodium hydroxide? And how do you know to put aqueous? Nitrate. And it actually tells you it's a solution. Do we know about the products? Is it going to be solid? We know that in advance? Okay, so one of the products at least will be a solid. So when you see reactants like this, this has a unique expression for this kind of reaction. Let's make it generic. Let's say this cation-anion pair, we'll define it as AB. And this cation-anion pair, different from the first, we'll define it as CD. When you have cation-anion pairs, or electrolytes, in solution, they can undergo what's called a double replacement reaction, which means consider them like dance partners. These two dance partners are having a good time on the dance floor. These two dance partners are having a good time. And then they switch. The cation from here wants to join the anion from here, leaving the cation from here available to join the anion from there. And so the products are going to be now an AD combination and a CB combination. And that's the name for that is a double replacement reaction. Or sometimes it's called a double displacement reaction. It displaces the cation and anion from another.
So what are going to be AlOH3S plus and NO3
Okay. AlOH3, and you're saying that's solid? And you know that because? Well, let's get the other product. What's your other product? Okay. So you're saying this is solid, and what makes you predict that?
Because of aluminum, like what you were talking about before, that it changes when you're dealing like with lead.
Well,
wasn't it
nitrate is
silver?
always aqueous.
Okay, so one quick way to fit, so you know one is going to be a precipitate. You know that nitrates are always aqueous. And so the other guy must be the precipitate. If you didn't remember all of the solubility rules, you could remember nitrates are going to be aqueous. Yeah, aluminum does drop out, is a solid, yes. So you're able to predict your products by knowing that it's a double replacement reaction. So how many reaction types have you encountered so far? You've not encountered a combustion reaction yet? Yes, Alex should have taught you a combustion reaction as we instructed it to. Nobody learned a combustion reaction in? Okay. So the kinds of reactions you'll run into soon: double replacement, single replacement, combustion reactions, neutralization reactions. Those are the first four before we get to the rest. And so one signature here, the double replacement, is the switching of the anion-cation with the other pair. Okay, so if this is your molecular equation, is it balanced? How do you balance it? So, my volunteer?
NaOH has 3, and then NaNO3 has 3.
Does that cover it? No? What's your suggestion? What do you want to change? Tell me, I'll put it here and we can work through it.
I'm not sure, but I think this OH is not balanced.
Okay. How come? So what this means here is that there are 3 OHs. And what this means here is that there are 3 OHs. Anything else? Yes? No? What? It's good. So we have a balanced molecular equation. Now we need to write the ionic equation. When do you usually take a break? Okay, right after this one we'll take a break. I mean all 3 pieces, the net ionic also. Okay, so the ionic equation. How would you write that?
Al
AL2 plus NO3 minus.
Keep going.
Na3 plus. Oh. I'm sorry. There's 3 Na plus.
ALOH3, solid.
Plus 3 Na plus. Plus 3 NO3 minus.
Like that? So basically the gist of it is that things that were aqueous will dissociate in solution, forming their respective cations and anions. And the thing that precipitates out stays as a solid. So now, can we identify our spectator ions, which are the same?
Plus one factor is Al3 plus aqueous and AlOH3 solid. That's what's in there.
That's what's left. So what do we do here?
Take out the 3 and A.
And 3 and 8.
Okay, anything else?
Take out the 3 and 8.
3 and
3 and 8.
So what's left would be the net ionic equation, which is Al3 plus aqueous plus OH minus aqueous AlOH3 solid. Right? Small break? Questions before the small break? How long is your break normally?